Voltage across the diode is equal to the negative voltage and current is 0. Diode position is turned off. Very good response. Keep on mute. Very good. Now the second switch is there, right? Here you can find a switch. That switch is called as SCR, silicon controlled rectifier, or in simple it is called as a thyristor. Okay. Thyristor or SCR, I will tell this, we'll discuss this in the next class. That I will tell you, they will not ask you about this. Now I will ask you about this third switch because that is known. Okay. This is known. Here I have a BZT in series with a diode. BZT in series with a diode. And there are three dots present. There are three dots present. Okay, na? A dot on the positive x-axis, on the positive current axis. Okay, dot on the positive voltage axis, a dot on the positive current axis, a dot on the negative current axis. Let us see what is the position. At each position, what is the condition of the switch? Now, let us take the first position. Let us take the first position. What is the first position of the switch? Here, voltage is positive, but current is 0. Why? Because I gave the positive voltage across the switch, combination of this BJT and a diode. But I don't give the base pulse. I didn't give the base current. Base current is 0. If the base current is 0, there is no control given to the switch. Therefore, what happens? The switch goes to off state. Even if I give a positive voltage, okay, there is no. If I give it is a simple. If it is a diode, what happens? The switch will turn on automatically. That's why you are getting. You are not getting this point on the positive voltage axis. Now you are getting a point on the positive voltage axis. Why? Because even if I give the positive voltage, the switch will not turn on, as if your mechanical switch. Even the supply is present, your fan will not turn on, right? You need to turn on the fan to get the airflow. Yes or no, the same thing. Even though the voltage across the switch is positive, the switch will not turn on unless until I give the control current. What is the control current? Nothing but the base current here. If I give the base pulse, what happens now? The switch will turn on and the point will shift to positive current axis where the voltage is 0, current is present. If we give the negative voltage, as you know, the diode will turn off and the switch will go to off state. That's why we are getting a point on the uh, negative voltage axis, means where the voltage is negative, current is 0. Because if I give a negative voltage, the diode will turn off. That's why we are getting the characteristics like this. Then this combination is called as a semi-controlled switch. You can turn on, but not turn off. We didn't say how to turn off. Okay, it is called as a semi-controlled switch. I think with this, we discussed much regarding the switching behavior, switching characteristics, condition of the switch when it is on, condition of the switch when it is off. Now there are 4 layers. Okay, 4 layers of semiconductors are present. P layer followed by N layer. In the case of a diode, there are 2 layers. P layer followed by N layer. But in the case of SCR, there will be 4 layers. P layer, N layer, P layer, and N layer. And there are 3 terminals. You can see 3 terminals. A represents the anode connected to the first P layer. K represents the cathode connected to the second N layer. And G represents the gate connected to the second P layer. Therefore, since there are 2 P layers and there are 2 N layers, let us name each layer as P1, this layer as P1. Now, this P layer, first P layer is called as P1. Now, the first layer P1 is called as, I named it as P1. First N layer, I'm naming it as N1. Second P layer, I'm naming it as P2. Second N layer, I'm naming it as N2. Now this is called as anode. This terminal is named as anode. Okay, A represented with A. This terminal is called as cathode. This terminal is called as gate. Three terminals are there: anode, cathode, and gate. Okay, three layers are there, three terminals are there, and four layers are there here. Okay, and because of four layer, three junctions are formed. J1 is formed between P1 and N1. J2. J2 is a junction formed between N1 and P2. J3 is a junction formed between P2 and N2. Okay. And let us see the widths of each layer and see the doping levels of each layer. If you see that uh, in this N2 layer, N2 layer is uh, if you see the N2 layer occupies very less space and heavily doped. N2 is heavily doped and occupies very less space. Even though in the figure, okay, it is a generalized figure for your understanding, it is drawn like this, but in practical, this N2 layer occupies very less space but heavily doped. This P2 layer is moderately doped and moderately spaced. Okay, na? It is light heavily doped. Sometimes it is called as heavy, even though it is heavily doped, but when compared to N2, the doping levels are somewhat less. That's why it is called as lightly heavily doped. Okay, light heavily doped junction layer is P2. Now N1 is very completely different compared to all. It occupies more space and very lightly doped. N1, see the N1. N1 occupies more space and it is lightly doped. P1 is similar to P2, means it occupies moderate space and moderately doped. Okay, now I'm again repeating again. N2 occupies very less space and heavily doped. N1 and N2 are exactly opposite. See that N1 and N2 are exactly opposite. P1 and P2 are behavior is similar. N1 is occupies more space and lightly doped. N2 occupies less space and heavily doped. P1 P1 occupies moderate space and moderately doped. P2 is moderately doped and occupies moderate space. Okay. Now, what about in what way doping levels is necessary to discuss? Okay. How doping levels will decide the functioning of the switch? Can anybody answer? How doping level? What is the need to discuss the doping levels? Because this is very very important. If you understand this doping levels only, I can understand the switching behavior of the SCR and which condition the switch will turn on, which condition the switch will turn off. If I understand these doping levels, why? Answer is very simple. Now, for example, if you see the J3 junction, J3 is a junction formed between two heavily doped regions. How much voltage it can block? J2 is a junction formed between one lightly doped, one moderately doped regions. What is the voltage it can block? Okay, now blocking means what? If I give a voltage, okay, I can consider P1 N1 as one diode, N1 P2 as one diode, P2 N2 as one diode. Okay, clear. Since the doping levels are different, we let us consider each junction as one diode. J1 junction as one PN junction diode. J2 as one PN junction diode. J3 as one PN junction diode. If you see that J3 is a junction formed between two heavily doped. If I add more and more doping levels, what happens to the, now I can say that this junction acts like a wall, and it will not allow flow of electrons or holes from one region to another region. It is called as a barrier. I think you have studied this in your electronics. The junction acts like a barrier. It prevents flow of electrons from one region to another region. It will not allow flow of holes from one region to another region because it is acting like a barrier. They are nothing but a wall. Now let us talk about each junction like a wall. Okay, a wall stopping the flow of electrons and holes. Now you tell me how much is the width of the wall in the case of J2 and J3. I'm adding, okay, doping means what? I'm adding impurities, means I'm adding holes concentration and electron concentration. I'm adding more number of electrons and more number of holes. Then what happens? Automatically the wall width will reduce. If I add less doping, okay, if I add less doping levels, means what? I'm adding less number of electrons and holes. Then what happens? Automatically, if the electron number and hole number is very less, okay, the junction width will be large. Okay, therefore, now that is the behavior which is useful for this. Okay, now that's why here, if you see this, if you visualize this, okay, I will take another thing and let us consider this SCR is forward biased. I will tell you what is meant by forward biased. Now I will give a positive voltage to the anode and negative voltage to the cathode. I'm giving a positive voltage. Now you can see, I think, okay. Now you can see that anode is connected to the positive terminal of the battery, cathode is connected to the negative terminal of the battery. Since anode is connected to the positive terminal of the battery, J1 is forward bias. Junction J1 is forward bias because P is connected to the positive terminal of the battery. Similarly, this N2 is connected to the negative terminal of the battery. Therefore, J3 is also forward biased. But if you see that J2 is reversed bias. N layer, which is closer to positive terminal of the battery, P layer is closer to negative terminal of the battery. Therefore, what is the condition of J1, J2, J3 when the SCR is forward biased? When the SCR is forward biased, what do you mean by forward biased? I can say that forward biased means the anode is connected to the positive terminal of the battery, cathode is connected to the negative terminal of the battery, then I can say that SCR is forward biased. When SCR is forward biased, J1 is forward biased. Okay, junction J1 is forward biased. J3 is forward biased. J2 is reversed biased. Since it is forward biased, it cannot block much voltage. Okay, this junction J1 cannot block the voltage. Okay, J3 cannot block the voltage. Therefore, what is blocking the flow of electrons and holes now? What is blocking the electrons and holes? J2. Now J2 acts like a very big wall, okay, and it will not allow electrons and hole movement from anode to cathode. That's why the switch condition is in off condition. That's why switch condition is off condition. Okay. Now let us reverse bias. Let us reverse bias the SCR. Let us reverse bias the SCR. Reverse bias means what? Now I will connect anode to negative terminal of the battery, cathode to positive terminal of the battery. Then what happens? See the junctions conditions. What is meant by reversed bias? Reversed bias means what? If anode is connected to the negative terminal of the battery, cathode is connected to the positive terminal of the battery. Okay, then I can say that now I'm connecting the anode to the negative terminal of the battery, cathode to the positive terminal of the battery. If anode is connected to the negative terminal of the battery, cathode is connected to the positive terminal of the battery. Okay, then what happens? The diode is the reversed bias. SCR is reversed bias. Then what about the What about the junctions? Let us see the junctions. If SCR is reversed bias, what happens to the junctions? J1. J1 is reversed bias or forward bias? Now P is connected to the negative. P is connected to negative positive. This P region is connected to the negative terminal of the battery. Is what?
Reverse bias.
Reversed bias. It is reversed bias RB. Now J3 N2 N layer is connected to the positive terminal of the battery. It is also reversed bias. Now J2, okay, N is connected to the negative terminal of the battery. P is connected to the positive terminal of the battery. It is forward bias.
Forward bias.
Okay, now you can see RB, FB, RB, right? Means J1 is forward bias, J1 is for reverse bias, J2 is forward bias, J3 is reverse bias. But as I said, no, J3 cannot block even though it is reverse bias. See that very, very important point here. Even though J3 is reversed bias, it cannot block the voltage. It cannot block voltage. Why? It cannot block the flow of electrons and holes because it is a junction formed between two heavily doped regions. Since it is a junction blocked between two heavily doped regions, J3 cannot block it. J3 cannot block the voltages. Only J2, as I said, no, it is forward bias. It cannot block any voltage or current. It cannot block the flow of current. Only what will block under reverse bias condition. Therefore, in reverse bias condition, J1 will block the flow of current. Therefore, in reverse bias condition also, SCR goes to off state without gate. I'm talking about without gate. Remember, okay, I'm talking without gate. Without gate, when SCR is forward bias, it acts like open switch because J2 is blocking the flow of electrons. When SCR is reversed bias, it is acting like open switch because J1 is blocking the flow of current. Okay, both in either condition, either in forward biased condition as well as in the reversed biased condition, SCR acts like a open switch. Okay, SCR acts like open switch. We are very near. Now, this thing, as I said, no, see the doping levels. ఇక్కడ చూడండి యానోడ్ ఎక్కడ ఉంది ఇందాక యానోడ్ మనం పైన ఉంది నౌ ఇట్ ఇస్ యానోడ్ ఇస్ ఇన్ ద బాటమ్ ఓకే దిస్ p layer p plus p అని ఉంది చూసారా దిస్ p layer is nothing but p1 layer this n layer is called as n1 layer this p layer is nothing but p2 layer this small region is there no, on either side. On either side, you can observe the small region. This is called as N2 layer. I'm repeating again. Can you see this now? Can you see the figure? See the width of each layer. What is the width of P1? 30 to 50 micrometers. Okay, 30 to 50. Now N1 layer 52,000. Okay. Next P2 layer 30 to 100. What about this? What about this N2 layer? 10. Okay, 10. You can see that 10 micrometers. Now you can see the width of each layer. Now this N1 occupies more space. Okay. This P1 and P2 occupies moderately space because it is in the range of 30 to 50. The other one is in the range of 30 to 100. But what about N2? N2 is just 10. Okay, very less space. It occupies less space. Now see the doping levels. 10 power 19 per cubic meter is the doping, okay, doping level. 10 power 19. It is for N2. See the case of this one. 5 into 10 power minus 14. No, P1 and P2, 10 power 17. See, I'm repeating again. N2, 10 power 19 per cubic per cubic centimeter. 10 power 19 represents the doping levels. Okay. Whereas in the case of P1 and P2, they are similar, 10 power 17. But in the case of N1, it is 10 power 14, means it is lightly doped. Okay, 10 power 13 to 10 power 14, it is lightly doped and occupies more space. I think everyone can see this, right? This figure, based upon this, we can understand. Next, you can see the different voltage, different SCR. This is one SCR. Normally, we use this type of SCRs in our laboratory. Okay. This is the SCR that is used for HVDC systems. Various ratings are SCR are available in the market. Voltage ratings are of 10 kV root mean square value, RMS value. Current ratings are of 30 kiloamperes. For handling capacity of 30 maximum rating. It doesn't mean that every SCR will have the same rating. Is heavily doped, N1 is lightly doped, N2 occupies very less space, N1 occupies more space. P1 and P2 are moderately doped and they are moderately spaced. And we have seen the construction, a physical construction also in terms of doping levels as well as in terms of the widths of the layers. Okay, this is a thing we covered in the previous class. And we have seen some important points during that. When SCR is forward biased without gate, I'm talking about without gate. When SCR is forward biased without gate, J1 and J2, J1 and J3 are forward biased, whereas J2 is reverse biased. Now, this reverse bias junction is acting like a barrier and it will block the flow of current from anode to cathode. Therefore, in the forward bias condition, okay, in the forward bias condition, I'm repeating again, in forward bias condition, J2 is responsible for blocking of the current. That's why it acts like an open switch. Without gate, when SCR is forward bias, it acts like open switch. Okay, just like an ordinary switch. In the case of a mechanical switch, what we are using for turning on the light or turning on the fan, unless until I press the switch will not be turned on. Similarly, like this only. Like this, the same thing in the case of SCR. If SCR is forward biased, it doesn't mean that SCR is on. The switch is on unless until I give the gate. Therefore, what is blocking the current is J2. In the case of reversed bias condition, J1 and J3 are reversed bias where J2 is forward biased. And here, as I said, no, P2 and N2 are heavily doped. Since they are heavily doped, what do you mean by doping? Adding holes and electrons. If they are heavily doped, number of electrons or number of holes in each region are very high. Even if I give a little bit energy, these electrons and holes can jump the wall, right? The more the number of electrons you are adding, the more the number of holes you are adding, the less will be the barrier width. Okay, now if it is just like if two people are in a room, enclosed room, nothing will happen. If 1,000 people are in a room, can the walls or the door can block the people? No, it's not possible. The same thing here. Okay. Now, therefore, J3 is not at all blocking the current. What is blocking the current is junction J1. Therefore, in reversed bias condition also, SCR acts like open switch. Okay, SCR acts like an open switch in the reversed bias condition. Okay, and we have seen the ratings of the SCRs also. There are variety of ratings available in the market. For example, if you want to buy any mobile phone, you can find number of varieties varying with prices, kind of features like that. Yes or no? In a similar manner, if I choose SCR, SCR is not a single device. You can find a variety of SCRs. The ratings varies from 600 volts to 10 kilovolts. Current varies from 10 amperes to 3 kiloamperes. Got it right? Yes. Now let us consider an SCR which can block a voltage up to 10 kilovolts. and the current it can block is 3 kiloamperes. Are you getting my point or not? Okay. Here I will take a switch. Okay, SCR is now a switch. Now what is the current it is blocking? What is the current value it is blocking? 3 kiloamperes of current. Okay. Now how much voltage it is? It can withstand 10 kilovolts. 10 kilovolts and 3 kiloamperes. Now to turn on this particular SCR, a gate current of approximately 0.5 amperes to 1 ampere is sufficient to turn on this SCR. That's why this current, gate current, is not a current, it is a signal, controlled signal. Are you getting this important point? Are you catching this? Are you understanding this important point? A current of a current of 1 ampere can control a current of 3 kiloamperes. That's why this is called as a gate signal. I think you understand this. Andrika అర్థమైంది కదండి ఈ పాయింట్. A current of a gate current of 1 milliampere to 1 ampere of current can control a current of 10 amps to 3 kiloamps of current. That is why this is called as a signal which can control, which can do on and off. Okay, this is about our SCR. Let us see the characteristics of the SCR, static VI characteristics of the SCR. Static VI characteristics of the SCR. For this, let us take a circuit like this. All of you draw this circuit. Here in this circuit, I have a SCR. Now here, this is the circuit for obtaining the VI characteristics of the SCR. The same thing is there in the laboratory also. You will do the laboratory experiment also. In the next semester, you have a power electronics lab. In this first experiment is obtaining the static VI characteristics of the SCR. For that case, let us take an SCR here. You can see the SCR. Now this is the SCR. Now here this is the anode. Okay. Now if you see the symbol of the SCR and symbol of the diode, what is the difference? Gate. Okay, na? Except gate, everything is same. Now why does it is given an arrow shape? Why the symbol is given an arrow shape? Because it always accepts current in anode to cathode. Current cannot flow in the reverse direction. Current can flow only from anode to cathode. Okay, that's why it is given the symbol arrow, like the diode. Can a reverse current can pass through the diode? Can a current, can high value of current can pass through cathode to anode? No. Similarly, in the case of SCR also, in the case of SCR also, current cannot pass from cathode to anode. Okay, that's why it is given the symbol arrow here. With the gate, the gate is used for turning on and off the switch. Now this is the supply, but here I want to vary the voltage. I want to vary the voltage and I want to check the behavior of the switch. Nothing but our SCR. For that, how do you vary a DC voltage? In two ways, either using a DC regulator, variable DC regulator power supply, or by using a circuit like this, a potential divider circuit like this. This circuit is used for varying the voltage, or you can go with a simple circuit where instead of this potential divider, you can go with a variable DC voltage. If you can vary the DC voltage with any DC regulator power supply, this configuration is not required. Okay, this is not required. Now load is nothing but a resistive load. I will connect some resistor, a load, or it can be a bulb, or it can be some device which consumes the energy. Now this is the switch. Now what about this circuit? What about this circuit? What about this circuit? Here, EZ, RG, S. For example, I have a switch in my room. Now, if I say the switch turn on, whether the switch will be turned on, no, you need to go there and you need to press the switch with the finger and you need to turn on. Okay, to turn on that, I require another operation, right? Now this is obtained. Now to turn on this switch, I require this particular switch. Now you can see now this circuit.
Yes, sir.
Okay, this EG, RG, S switch. Okay, this combination is used for turning on this particular switch. Okay, think like a switch. This is like a switch. Okay, think SCR. Imagine SCR like a switch. Okay, imagine SCR like a switch. Now tell me whether it is forward biased or reverse biased. Now it is forward biased. Why it is forward biased? If you see that anode is connected to positive terminal of the battery. Cathode is connected to negative terminal of the battery. With this circuit, I am connecting the SCR in forward biased condition. In forward biased condition, okay, as I said, no, J1, junction J1 and J3 are forward biased, whereas the junction J2 is reverse biased. Now, this J2 will block the current so that SCR acts like open switch. This is what I said, no, this is for an ideal condition. But practically what happened, this is a semiconductor switch, not a mechanical switch. This is a semiconductor switch. Even junctions are present, some leakage current will pass. Okay, now some leakage current will pass from anode to cathode. Okay, now don't feel that it acts like open switch means the current cannot pass. Got it right or wrong? Okay, now since it is a semiconductor switch, don't feel that the current is zero. Some leakage current will be passing. Now, if I increase this voltage, positive voltage connected, okay, anode to cathode voltage. If I increase that anode to cathode voltage, that leakage current will also increase. Okay, na? The leakage current is because of the flow of the minority charge carriers. You know that in the case of a diode also, okay, before cutting voltage, ideally, diode acts like open switch, current should be zero. But practically what happens, some microamperes of current will be passing from anode to cathode in the case of a diode. You done this experiment in the case of electronics lab. Have you done that experiment? Diode VI characteristics, have you obtained? Diode VI characteristics.
Yes, sir.
Yes. From up to cut-in voltage 0.7 volts, actually current should be zero. Ideally, current should be zero. But practically, if you do you observe that current is zero? No. Some microamperes of current is passing. Similarly, in the case of this SCR also, okay, even as I said, no, J2 is blocking the current, but still it is a semiconductor switch, not a mechanical switch. The regions are not isolated. The regions are okay separated by junctions. If the regions are isolated, current will be zero. But these regions are not isolated. They are separated. Okay, just like our Telangana and Andhra. Okay, they are separated, not isolated. Okay, there is a difference. Therefore, since they are separated, okay, some leakage current will be passing from anode to cathode. Okay, because of this leakage current, then that leakage current will increase with increase in the voltage. When you increase the voltage, what happens? You are increasing energy. You are giving more and more energy to the charge carriers. What are the charge carriers? Electrons and holes. I'm giving more and more energy. Therefore, what happens? The electrons and holes will acquire more and more energy and will jump the wall and it will bypass the junction. Okay, if I give more and more energy, what will happen? Okay, more and more electrons will jump and the current will also increase, but still that current is still leakage current. Okay, now therefore you can obtain you can see the characteristics. You can see the characteristics in this figure. Okay, can you visualize this figure VA characteristics? Can you visualize this figure VA characteristics? Yes or no? For example, if the full load current is 10 milliampere, if microamperes of current is passing through the switch, I consider that current as zero. The current is zero. Okay, it is considered as an open switch. This region, what I have highlighted, is called as forward blocking region or forward blocking mode. Okay, the reason what I have highlighted in the figure is called as forward blocking mode. Why it is called as forward blocking mode? It is because in this region, during this period, even the SCR is forward bias, J2 is blocking the current, and some leakage current is passing, but still SCR acts like open switch. That's why it is called as what you have done. Okay, you have forwarded the SCR, you have forward biased the SCR, but it is under blocking state. That's why it is called as forward blocking mode. Okay, forward blocking mode. Everybody understood that? Okay. Now I'm still increasing the voltage. I'm go on increasing the voltage. As I said, no, if I increase the voltage, I'm giving more and more energy to the electrons and holes. Now, when electrons and holes receives that energy, some of the electrons will get sufficient energy, will jump the wall. What is the wall here? What is the wall here? The wall is nothing but the junction J2. Wall అంటే సార్ వేర్ ఇస్ ద వాల్ డోంట్ ఆస్క్ ది క్వశ్చన్స్ ఓకే వాల్ అంటే అర్థమవుతుంది కదా ఐ థింక్ ఇన్ అవర్ లాంగ్వేజ్ ఇట్ ఈస్ వాల్ ఇన్ సెమీ కండక్టర్ లాంగ్వేజ్ ఇట్ ఈస్ కాల్డ్ as barrier okay whatever may be the case it is I feel like a wall now that wall is blocking or I can take this SCR I used to compare SCR with like a dam okay consider SCR like a dam on one side huge amount of water will be there okay there will be walls blocking that flow of water okay dam walls will block the water flow now there is a gate okay which can control the flow of water if the gates are blocked you can observe that there is little bit water flowing from one region to other region that is called as a leakage current since the leakage that is called as leakage water right if the dam gates are closed don't feel that the entire water will be blocked some current little bit current is passing okay from one side to the other side because of this water do you agree that water is flowing no we'll say that water is stopped yes or no the same case here the same case here okay now one side, now this junction J2 is acting like a gate of the dam. Okay, this J2 is blocking the flow of water. Similarly, here J2 is blocking the flow of current. I think are you able to understand this SCR behavior with the dam? Okay, remember SCR like a dam, then you can understand it. Okay, now what happens now? I'm increasing the voltage. Increasing the voltage, it means that increasing the energy. Okay, it is like that increasing the water levels on one side. Okay, now on one side, what happens? Water will be stored. If the water level is increasing, what happens? At one point of time, what will happen? The height of the water is exceeding the height of the wall, what will happen? Okay, water, okay, these gates cannot block the flow of current. Do you agree or disagree? నేను చెప్పిన ఎగ్జాంపుల్ అర్థమైందా అర్థం వల్ల చెప్పండి ఐ లాస్ట్ ది స్టూడెంట్స్ అనిల్ కుమార్ you understand the example what I have quoted now increasing the voltage applied anode to cathode voltage is like increasing the water level of the dam okay now water level of the dam is increasing at one point of time what happens
Water will comes out, sir.
water will be height of the water will be more than the water height of the dam then what happens now tell me this walls of the dam can stop the water the gate can stop the water no
Yes, sir.
no okay similarly in the case of the SCR also thank you Anil Kumar keep on mute. Now, in the case of the SCR also, there is a voltage called as VB not forward breakover voltage. Spelling తప్పు ఉందని చూడండి ఇక్కడ నెట్ ని తీసని ఫిగర్ ని there are certain wrongs in the figure don't think that what is there in the figure is correct forward spelling is wrong here okay VB not if the applied voltage VB not is higher than the forward breakover voltage. Okay, what happens? Avalanche breakdown will take place. These electrons and holes will acquire more and more energy. They will break the wall and will jump from anode to cathode. No walls, no barriers cannot stop them. Okay, no barriers, no walls, nothing can stop them. That particular voltage is called as VB naught. Okay, what is that VB naught voltage? It is a voltage above which, okay, current flows from anode to cathode without the gate. But is it the correct way of turning on the SCR? For example, is it I considered this example of the SCR with the example of the dam. For example, water level of the dam is increasing at one point of time. Recently, I observed that 5 years back, I think. There is an incident happened in Nagarjuna Sagar where water has reached beyond the level of the dam. But is it the correct way of handling the dam? No. Why? What happens? If you operate every time like that, what happens if you see that every time you will close the dam gates until the water level reaches the height of the walls? Is it the correct way of operation of the dam? Now here I will apply the voltage like this. I'm applying a positive voltage to P2 and negative voltage to N2. Okay. Now can you see that thing what I've drawn in the red color? Can you visualize? Can you
Yes, sir.
visualize? Yes. Okay. I'm giving the voltage. Okay. Positive voltage to P2 and extra. This is the extra voltage I'm talking about. Okay. I'm giving a positive voltage to P2 and negative voltage to N2. What happens now? I'm giving the voltage means that giving energy. Okay. If I give energy, what happens? What is there in the N2 region? N2 region is heavily doped. And in the N2 region, what are there? One second. In the N2 region, lot many electrons are present. Many electrons are present. Huge number of electrons are present in N2 region. Now, if I give some energy, the region, the junction J3 is very less. Okay, it is a very small wall. Okay, therefore, what about now? These electrons will move. These electrons will move to the P2 region. After moving to the P2 region, what happens? They will reach to the J2. They will reach the which junction? J2 junction. They will reach the J2 junction. What is present in the J2 junction? Positive ions are present. Now, what they will do? They will interact with the positive ions. Ions will disappear. Now, here at this point of time, I gave the voltage. After giving the voltage, what happened? The current increases like this. Current increases like this and reaches a current called as the latching current. Okay. Once it reaches the latching current, I can say that the switch is completely turned on. Okay, ఇది latching అండి కెన్ అన్నది హోల్డింగ్ ఓకే ఇక్కడ రివర్స్ లో ఉంది చిన్న మిస్టేక్ ఉంది ఇక్కడ కరెక్ట్ చేసుకోవాలి దిస్ కాల్డ్ యాజ్ ది latching current. For example, current after giving the gate voltage, as I said, no, what is blocking the current? J2. Once, okay, if I give the gate current, the J2 will not vanish suddenly. It vanishes slowly. Okay. When it vanishes slowly, what happens? As if the gates are open. Now, if I open the gates will open at a time or they will slowly move up. Dam gates ఉన్నాయండి. I'm opening the dam gates. Dam gates open at a time or they will slowly open. ఏం జరుగుతుంది చెప్పండి ఒకసారి. What will happen? Now, when I gave the gate voltage, okay, the region will not, the J2 wall will not vanish at a time. It will slowly vanish. Now, it will first vanish at the point very closer to gate. Later, it will goes on expanding. That conduction region will expand. Okay, the conduction region, I can say that now initially small space will be provided. Later, the space will increase, the conduction space will increase, and completely later what happens? The conduction space will spread over the entire region so that there is nothing to block the flow of current.